Hi, this is episode 6 of my PSU design series, and in this episode it's a continuation of the linear basics, and in this part we'll be discussing the operational amplifiers, or OPAMPs for short. And today mainly we'll be focusing on the LM358, which is a dual op-amp in a single package, and I have one here to show you. Okay, so here we have two packages of the LM358. So I'm holding a light close so you can read the code on the in the SOIC package, which is the this one here, SOIC, and that's the surface mount. You see how small it is next to my finger. And and this is the dip package. Let me just turn this light off. And before we move on to the next section, I first need to discuss about the power supplies, or where we get the 0 volts or the common from. Now, on a bipolar power supply you have the positive voltage out, a common, and a negative voltage out. Basically all it is, is just think of it. If it was batteries, this is what you would have, and this is a variable. So basically, where two batteries would join, the positive and negative join together, that would be your common. And then, in reference to common, this would be positive, and this would be negative. And this is the power supply that would be happening for using the bipolar method of using the op-amps. Alternatively, if you only have a single supply, you can create a virtual ground, a virtual common, using your using two resistors. Let's say 10k and 10k. You'd have to check the current, but with these both being the same, this point in reference to here would be plus V divided by 2. So therefore, if this was 12 volts, this would be 6 volts. Or positive 6 volts common, negative 6 volts, and there you have your split supply, so you can do your op-amp circuits. Now, as you can see in the diagram, we have two separate operational amplifiers in the package. This here goes to the positive voltage and this goes to the negative voltage. Now, if we're doing a bipolar supply, this will go to your positive volts and this will go to the negative volts. If you're doing a single supply, this will go to the positive and this will go to ground. And there isn't a ground pin on the package. That's because the ground is set by the power supply itself. This chip doesn't care where the ground is. It's just the calculations for the outputs depend on you knowing where the ground is. Okay. The simple operation of an op-amp, no matter what circuit it's in, we have the positive, also the non-inverting input, and we have the inverting input. And what it is the difference between this. So the voltage on here, subtract the voltage from here, and then they multiply that by the internal gain of the op-amp, which is usually really high, like in the 200,000 range. So say we had 2 volts here and 1 volt here, so 2 minus 1 is positive 1 multiplied by 200,000 volts. So there's about 200,000 volts expected out, but it will not be any higher than VCC, or it'll be a little lower than VCC, but it'll be clipped by the saturation of the chip in whatever direction. And if you have the bipolar supply on here, and you have 1 volt here, and 2 volts here, then 1 minus 2 is minus 1, so you'll get minus 1 volts out. But if you have this going to ground, then it'll be clipped at the saturation, which will be 0 in this case. But that's an open loop configuration. I'll explain that a bit more in the next bit of information. But for now, yeah, this is the wonderful device. Let's see if I can get you a close-up view of it. Okay, it's just a standard 8-pin package, average jelly bean device. You'll find these in all sorts of products. Oh, come on, where are we? There we go. LM358. Yeah, they may be in different packages, but the die inside is exactly the same. It's just wired out to a different package. Okay, let's move on to a bit more theory. With the operational amplifier, we have to assume a few things, unless you know exactly what's going on the inside, which I don't myself. I was never taught that, and I never really needed to know that. But yeah, the things you need to assume with this is the input impedance will be as close to infinite as possible. As close as possible to infinite, and therefore any current flowing through into there should be as close as possible to 0 amps. Therefore you can use these theoretically to connect to circuits, and it should not interfere with the input, the output of the circuit, by loading effects and such. Now the output resistance is therefore supposed to be as low as possible. Okay. And okay, so the basic operation of the OPAMP, the formula needed, see, so V out is equal to the positive in subtract the negative in, right, multiplied by the gain of the open loop, which I'd say could be in excess of 200,000. And that's obviously limited by your supply lines. Now your saturation points will be slightly below these supply lines because the internal resistances and such from the op-amp itself. So your saturation levels, as they're called, say like on the this is the LM358. Sorry, I'll put A then. It's actually 1/2 of it. Let's say you had this at 12 volts, you'd probably get around about 10.5 to 11 volts positive saturation, and this was negative 12. You'd probably class like 10.7 to like 11.5. It's been a while since I've used this device, so these figures vary depending on the actual op-amp you use, so plan well when you use it. Oh, sorry. Now this is basically used in a comparator sort of configuration here when it's an open loop, because the gain basically the difference of here is amplified by 200,000. So whatever difference here is amplified to either a full on, a full positive, or full negative signal, depending on your inputs. Now that may not be useful to everybody, so we have feedback on these. Bear with me. Okay. Okay. What we have here is a basic feedback circuit. This is a negative feedback, and the formula for this, that's RF, that's RI, is basically RF over RI. It's a negative of that. That's the multiplied by Vn. So this is Vn. Okay, so V out equals that. And this will give you the output required for that. The next circuit configuration I want to show you is the non-inverting amplifier. Zoom that in a bit. Now here the input is coming in to the non-inverting input rather than the inverting input, and where the input was in before, we now got to the common, or the 0 volts, whichever you want to call it. Now the formula for this is V out equals 1 plus RF over RI, all that multiplied by the V in, and that will give you a positive going amplification. Now this circuit could be used for audio amplification. You have to find the correct matching op-amp for that. The LM386 is a commonly used one for audio amplification. And now here we have a multi-channel or a mixing input type configuration. This is the inverting amplifier configuration. So basically it will mix the two inputs and it'll amplify it accordingly. Let's write these. Now a lot of people are a little put off when they see the circuit, but it's actually quite a simple one. And okay, so let's see what the formula looks like. Now basically V out. Now you will be working this in two parts. So basically you ignore that, then you work it out as a normal inverting amplifier. You take that result, and then you work that as a normal inverting amplifier. You take that result and you add them together. So basically it's minus RF over RI1 in this case, multiplied by V in 1 plus minus RF over RI2 multiplied by V in 2. There. And that's the formula. So that will sum. It's also called a summing amplifier, and that will sum the two together and it'll make it negative. So basically what you could do is you could then just stick it in back in for another inverting amplifier, and make sure that these two values are equal, so it will give a gain of -1, so it will just invert this, and therefore this will become a positive version of just this. Here we have what they call a unity gain buffer. It's called a unity gain buffer because it has a gain of 1, and it's non-inverting, so basically V out equals V in. Now the benefit of this circuit is because this is a high impedance input, it doesn't load the previous stage. So to say, if which we'll be using it in our power supply for sensing the V out. So say you got your voltage line going out, we basically can tap onto it, and as long as it doesn't exceed the voltage rails of this op-amp. See, I don't draw them in. We basically assume the voltage on this. Let's just say for sake, +12 and 0 volts in this. So as long as this doesn't exceed, so it's less than 12 volts, then whatever's on here will be present on here, and it will not load down this circuit. Or in practicality it will, but it'll be very minuscule and barely, not really worth worrying about in this case. But yeah, this can also be used to amplify a signal with a low current drive coming out of it as well. So you could, so then this can be used to push into more things that require a bit more current than this is capable of driving. Whichever, there's so many different ways to do it, that one. Now this circuit here is a little bit more complicated. This is the differential amplifier circuit. Now we'll be using this, we'll be experimenting with this with the current sensing routines. Basically we'll be putting a shunt resistor through here and measuring the current going through it using the voltage drop, then multiplying it by the resistor to calculate the current going through it. But you'll see here some duplicate markings. This is RB and RB. These are both identical values. Same with RA and RA. Now the formula for this one is as such. So V out equals V2 subtract V1. All that is multiplied by RA over RB, and that will get you the gain, the difference of this multiplied by the ratio of the two resistors. Basically, if you put all four of these resistors the exact same value, you would get out just the difference of this. But if you configure this to be like 10 times or 100 times, depending on how you want to do it, which is great, because when we're doing the current sensing using a shunt resistor, we're talking like millivolts that we're trying to read here. So we need to multiply it by the hundreds or maybe even the thousands, depending on the shunt resistor we choose. There are a few more configurations with these op-amps that you can turn them into low pass, high pass and band pass active filters, but that's a little bit out of my depth for me, unfortunately. So I'd refer you to elsewhere on the internet to find that kind of information. All I deal with is the amplification side, basically using it for inverting and non-inverting input and unity gain input, as well as the differential and the summing of inputs. That's but yeah, that's the only use they are for me. In the next analog video, I'll be showing you one more configuration I haven't highlighted here, which will be the voltage regulation, and we'll be using this little puppy here. I don't know if it shows well on the camera. Well, that is a 2N3055. It's an NPN power transistor. I'll be using this in conjunction with this to do voltage regulation. That will be in the next analog video, 2 videos time. However, in the next video we'll be looking at the Hitachi based LCD screens and driving them with the Arduino. This will provide our display for the power supply, and yeah, it's quite a simple little device. You can either run it with 4 data bits or 8 data bits plus a couple of other control lines, but that's for the next video. There'll be more on that to come. Okay, so that concludes this episode. We found this this little mini tutorial, I suppose, on the operational amplifier helpful. It's by no means exhaustive. There's plenty of exhaustive examples on the internet out there. Dave Jones did a really good one. I'll probably link him in as well for that one. I'm basically just covering enough information to act as a building block for the power supply project, and yeah, the information is, as far as I'm aware, accurate. I will double check. If I've made any mistakes, I'll definitely annotate it and let you know. But all the formulas I will include below in the description, and yeah, all the circuits I will also put onto my website, which I'll be doing shortly after I've uploaded this video. So if you're watching this video when it's fresh out and it's not there, it'll be there in the next day or two. And so yeah, so this is the end of the episode, and I thank you for watching, and please like this video. Lets me know that I'm doing a good job, and if you haven't already done so, please subscribe. Have a good night. Bye.